Yeah, so alkenes are the first unsaturated compound that you're going to look at. We already know from O levels that they have a carbon-carbon double bond. You can't just say they have a double bond because carbon-carbon double bond is the distinct thing that separates them from alkenes. Just like alkenes, they have cyclic alkenes and they also have many isomers. And the difference is that they have fewer hydrogen atoms than the alkenes. So, for example, butane has 10 hydrogens, but butene, whether it's butanene or butene, which are two isomers of butene, it has 8 hydrogens. So, alkenes usually have double the number of carbon as hydrogen in straight chain compounds. So, we call them unsaturated because they have double bonds in them. And that's because that double bond can be broken down and you can add more hydrogen atoms. So they're not completely saturated. So that's why. Uh, the molecular formula, general formula is something that you have already seen in O levels again. That's nothing new for you. So the general formula of alkenes, I'm talking about the straight chain ones, is CnH2n. Or I can also say that this is CH2 times N. And they're both the same thing. So all you're doing is you're taking CH2 and CH2 resonates with the homologous series because in every homologous series, the next member differ from the previous one by CH2. So that's something interesting that the general formula of alkenes is also CH2 times N. You should be able to draw isomers of at least the first 5 alkenes that you have. And one reason why their structure is different is because of the bond angles of carbon. Now, every time carbon has a double bond, the hybridization, if you remember from atomic structure, we talked about hybridization. We said that some orbitals were overlapping with the others, and there were some electrons were promoted, and you created hybrid orbitals. So because of that, what you have right now is you have 3 sigma particles, right? Sorry, 3 sigma bonds, 1, 2, and 3. And there's one pi bond. Pi bond is the double bond that you get. So if I'm talking about this carbon, it has 3 sigma bonds. So the number of sigma bonds tells me what kind of hybridization it has. So this one has 3 hybrid orbitals, which means that it is sp2 hybridized. There's s and there's 2 p orbitals that make this sp2 hybridization possible. And that's why the bond angle over here would be 120 and the molecule would be trigonal planar, not tetrahedral as is the case in alkanes. Again, this is only for the double bond ones. Of those that don't have a double bond carbon atoms, they will still be sp3 hybridized if they have 4 bonds. The difference in hydrogen and carbon's electronegativity isn't much. So they're pretty non-polar, which means the dominant force of attraction, intermolecular force of attraction, is coming from van der Waals forces or London dispersion forces, which we call them. So van der Waals are the major forces, which means that because these are weak forces, they are volatile, they have low density, low melting point, and all of the things that we usually see. Okay. Also, they have low solubility in water, and that's again because they cannot form hydrogen bonds with water. The main factor or the main characteristic of alkenes, and that's the thing you should basically know about, is this pi bond. This pi bond is different from the sigma bond in the sense that in the sigma bond, electrons are not delocalized as they are in the pi bond. What that means is that electron in the pi cloud or electron in the pi bond, they have more freedom to move around. The electrons in the sigma bond are more limited. So the blue oval over there is supposed to show the movement of sigma electrons, but the ones that are in the pi, they're much more free to move around, which is why these electrons attack any thing with a remotely positive charge. So anything that comes close to this with a positive charge, and remember that things with positive charge are called electrophiles. So these can attack electrophiles. And that is the characteristic of alkenes, that they have pi electrons which are delocalized. There is high electron density in there. So what they can do is that they can attack anything with a positive or even slight positive charge. And that is what happens when acids or water or even bromine or chlorine molecules approach them. As the dipoles are created, remember dipoles are partial charges. As the dipoles are created, these pi electrons get attracted to them and they can easily attack the dipoles. And that's the primary mode of reaction of these alkenes. They have pi electrons which are delocalized and they are able to attack anything which is electrophilic. Okay, so high electron density makes it easy to attack positive things. That's pretty straightforward, right? Positive attracts negative. No, who doesn't know that? And that's exactly what's happening here. Positive attracts negative. And you have negative electrons in there that are moving around, buzzing around, looking for those positive things to attack. And that's what they do. These will attack electrophiles. So I'll give an example. Let's say I have ethene is like this, and this has these pi electrons moving around. Let's say, and these pi electrons are delocalized, which means there's pretty large area around them where you can get these pi electrons. Okay, now let's suppose an HBr atom approaches it. So HBr, what's that like? H is slightly positive, Br is slightly negative. And as soon as this comes close to it, it gets realigned. What's happening is that this HBr, the positive side will be attracted very strongly towards the pi electrons. So what happens is that it realigns in the way that the negative side is pushed away and the positive side gets closer or more attracted to these negative electrons. Okay, now what will happen? These negative electrons will obviously be attracted to the slightly positive charge, and we show that through this curly arrow. This curly arrow shows that these pi electrons, and usually we draw the curly arrow from the double bond, so these pi electrons will attack this electron, this slight positive charge over here. All right, so that's what happens. Now imagine electrons advancing towards positive charge. What will happen to the electrons that are already next to hydrogen? They will be repelled. There is a host of electrons coming towards this H slightly positive charge. And then obviously any electrons that are in the vicinity of that thing are going to retreat. Those electrons are pushed back towards the more electronegative bromide. And this is the first attack happening from the pi cloud. So remember, the curly arrow always shows direction of electron pairs. They always show movement or attack of electrons or electron pairs. If it's a half curly arrow, that's electron. If it's a full curly arrow, that's electron pair. But this electron pair is attacking the slightly positive charge. Why? Because positive attracts negative. That's a fundamental law. Okay, that's it. That's the decisive factor here. So when they come close to it, it pushes the electrons that are close to hydrogen away, which then go towards bromide. What happens? What happens if hydrogen were to simply lose those electrons to bromine? Heterolytic fission. That's what happens. So in a way, what happens is that this bond, which was with carbon and carbon, is suddenly realigned towards this hydrogen. So while over here, carbon was sharing one electron with this one, both of these electrons are now attacking hydrogen. And because of that, hydrogen will be joined with one of these two carbons. So one of the carbons in here is going to get that hydrogen. Now, hydrogen does not have a charge. Why not? Because it lost one electron that it had to bromine, but it gained the two electrons that were here. So that way, the electron it lost has been compensated by the electron from the carbon. So carbon kind of made a dative one by heterolytic fission of HBr. Okay, what happens to the bromide? Bromide is there with the lone pair, negative charge. And what happens to the carbon that lost an electron? Remember that this carbon had basically two electrons that were being shared, and suddenly they both attack this. So one of them was given to hydrogen and one of them was shared with hydrogen. This carbon, one of them lost an electron, which is why that will have a positive charge. And now this thing is as old as time itself. This lone pair is going to attack this positive charge. That's a no-brainer. Negative attracts positive wherever it sees it. That's exactly what happened here. The electrons in the electron cloud, the pi cloud, were free to move around, so they attacked the slightly positive charge in hydrogen. This will be a slow step because they're slightly positive. But the second one is pretty fast because you have a full positive and a full negative charge, and they are going to snap together like very strong magnets. And what you're going to end up with is what we call electrophilic addition. And this diagram, that's called a mechanism. That is a story of how the reaction happens. Again, remember, if you are clear about this idea that lone pairs will attack positive charges, or freely moving electrons will attack positive charges, or slightly delocalized electrons will attack positive charges, you will have absolutely no trouble in understanding almost every uh, organic reaction. At the heart of every organic reaction, the idea is positive attacks negative, negative attacks positive. That isn't difficult, right? We know that positive will attack negative, negative will attack positive. But the story comes from electrons. That is why we always say electrons attack it. It's not the positive that initiates it. We always say electrons are attacking. Okay. And that is why the curly arrows show the movement of electrons. So in any reaction, you start by understanding where are more electrons, what thing is electron rich, what thing has a high electron density. And that thing is going to attack anywhere you have slight positive charges. The more the positive charge, the more faster or stronger the attack. Okay. And that is electrophilic addition. So this thing in the middle, this one over here, this is called intermediate. This is the thing that is made during a reaction. It doesn't stay for a long time. It just forms and goes away. And this thing over here, the carbon with a positive charge, is called carbocation. Okay. It is a carbon with a positive charge. And of course, it's a positive charge because there is heterolytic fission. This bond broke, the carbon lost an electron. Where did that go? To the hydrogen. But what about the hydrogen's own electron? That went to bromine, which is why it has a lone pair. So all that's happening is rearrangement of electrons. Hydrogen got an electron from the carbon, carbon lost it, so it became positive. Bromine got an electron from hydrogen, so that way it became negative. And that negative and that positive on carbon, they just bonded together and lived happily ever after. All right, let's take another example. What if I don't have something that's slightly positive charge? Does that still work? Like, what if I have something? Maybe I can blame the slight positive charge on HBr over here. That HBr is a polar molecule, and that's why it happened. Let's see if it works without that. What if I have an ethene again? Sure, there is delocalized electrons moving around. The pi cloud is there. But what if a pretty straightforward hydrogen atom were to approach it? Again, as soon as hydrogen approaches it, hydrogen has its own electron cloud. There are two electrons there, right? So the electrons are going to be pushed away from the cloud. And it is going to cause a dipole. The electrons are going to be pushed towards the hydrogen that's further away. So you are going to get a slight positive and a slight negative charge. And what happens now? The moment you get a slight positive and a slight negative charge, electrons have a way. They will attack this hydrogen because negative attacks positive. That's it. That's a law of nature. Negative attacks positive. So you get that dipole, and now it's going to attack. And now what are we going to get? One of the carbons is going to attach itself with this hydrogen, causing the hydrogen's own electrons to go further away. Because as those electrons approach, these electrons retreat. And then you have this thing here. I'll use a different color. So you have an intermediate formed. Okay. And this hydrogen now has an extra electron and a negative charge. So, and that carbon has lost a positive. And what happens? It attacks this. That's it. And you are left with ethane, electrophilic addition. The reason addition is possible here is because you have electron pairs that are in the pi cloud, they're easy to move around and all. Now, this is pretty simple. What if I had, how would I know which carbon will get more electron? Which carbon is more likely to get the hydrogen? How do I know that? Then remember that the reason the electrons are coming, or the reason hydrogen is coming towards a carbon, is because that carbon has electrons that it's providing. The more electrons something has to provide, or more negative something appears to be, more likely it is to get that hydrogen. So what does that mean? Anything that can sustain a negative charge for long will be more, will be a better place for any hydrogen to come to. So how does that tell me what's going to happen? So remember one thing, that alkyls have an inductive effect. So for example, if I had double bond here, okay, this is a good example. Okay, so I have a double bond here, and in this case what I have is that this carbon is primary carbon and this carbon is secondary carbon. Now the primary carbon is the secondary carbon is getting an alkyl effect from this one and this one. There's a positive inductive effect coming from two of these, which makes this a better carbocation. Okay, positive inductive effect allows for a more stable carbocation. Why? Because if it gets a positive charge, it can sustain that for longer because other alkyls are providing it with the electrons that it needs. It's not going to go crazy that, oh my God, I have positive charge, I need to get electrons, and so it disappears right away or breaks back. It doesn't. It can sustain that positive charge. It can hold on to that positive charge because it has support of the other alkyl groups, other activity groups. If it had a chlorine next to it, it will be even better because chlorine is electron with, it can be an activating group. All right, so what happens here? Now, there's two options. When anything approaches this, let's suppose HBr approaches this, then HBr is going to have slightly positive charge here, slightly negative charge here. And no doubt that this pi electron is going to approach it, attack it, and going to push the bromine bond, the hydrogen bromide bond away. No doubt in that. But there's two options I get. One option is that the left carbon becomes a positive charge and the carbon goes in the middle one, the secondary carbon. That's one option. The second option is that carbon goes to the first carbon, the hydrogen goes to the first carbon, and the second carbon gets a carbocation. And there you go. Now think about it. Which carbocation is more stable? Because it has inductive effect from two of them. 1, 2. They're both providing it with negative electrons, and now it's able to sustain that positive charge for long. But over here, you just have one, the inductive effect of just ethyl. Sure, ethyl will have a bigger inductive effect from methyl, but this is two methyls. So the inductive effect of the both of them methyls counteracts or exceeds the inductive effect of one ethyl. And that is why this is a more stable one, more stable carbocation, which is why the hydrogen is not going to go here. Carbocation is going to form here, which means bromide gets to attack the carbocation now. And this one is a better option. That is why when you're done with the reaction, you will see that while this is produced, of course, you will do fractional distillation to separate it. You will notice that this is produced more. And we call this our major product. And we call this our minor product. Now, again, the reasoning is pretty straightforward. Anything that can sustain the carbocation for longer gets to be the major product. Why would, and what helps in becoming a more stable carbocation? Having an inductive effect around you. So if there's more alkyl, if this was a tertiary carbon, it's no question that this will definitely be the more stable carbocation. Okay, so but we don't always have time to figure this out, that which is more stable, which is less stable, what is more likely to become carbocation and what is less likely to become carbocation. We don't have that, right? So we have a shortcut to figure this out. We call that Markovnikov's rule. Markovnikov's rule. And Markovnikov's rule is a really good way of looking at this thing. Markovnikov's rule says that hydrogen goes where there's more hydrogen already. Think about it. On the left carbon, there is two hydrogen. And if the new hydrogen goes over there, that's going to be my major product. In the middle carbon, I have one hydrogen. So hydrogen, if it goes there, that will be my minor product. And that's Markovnikov's rule. It's a really simple way of understanding this, that hydrogen goes where there is more hydrogen already. Okay, so remember this. Whenever you're adding acids or water or something with hydrogen, hydrogen goes where there is more hydrogen already. And again, Markovnikov's rule is just telling us the same thing. Instead of talking about uh, the stability of carbocation, it is explaining, it's not really explaining, it's just telling us where the hydrogen will go. Okay. Of course, it doesn't work for things where you don't have hydrogen. Okay. If you have like chlorine and bromine, then of course this doesn't apply. Okay. Another way of looking at the Markovnikov's rule is that the more negative thing goes to the carbon with more carbons in it. The more negative thing, like in this case, it's bromine, the bromine, which is more negative, goes to the carbon with more carbons. So obviously, the carbon on the left side has just one carbon next to it, and that's primary. So compared to the middle one, which is secondary, secondary is going to get the more negative thing. Why? Because again, it is more stable carbocation. So why wouldn't you attack the more negative thing? Okay, so that's another way of looking at Markovnikov's rule. And this one is more general because now you don't have to figure out where hydrogen goes. You can just figure out that, all right, what is more negative? And that thing will go to the carbon with more carbons next to it. So if you have a tertiary one, that wins. If you have a secondary one, that wins. And if you have a primary one, of course, if all you have is a primary one, then it doesn't matter. Okay, so Markovnikov's rule, if I were to write it down, then there's two cases. One is when you're adding hydrogen. So it says that hydrogen goes to the atom with more hydrogens already. That's one way of looking at it. Or the negative way, or the other way of looking at it is that the more negative species goes to the carbon with more carbons next to it or joined to it. So two ways of looking at Markovnikovs. Again, things that don't have carbocations, like the free radical substitution we talked about, Markovnikov's rule doesn't matter over there. Okay, so free radical substitution that we see, that has nothing to do with Markovnikov's rule. But Markovnikov's rule works if you have presence of carbocations. Okay, so that is Markovnikov's rule. Okay, so now we are ready to move on to understanding different options and considering different options. So here's my question to you. We have, we are trying to add, so here's the thing. I have this thing, propene, and I want to react it with bromine. Show the mechanism of what happens and what I get at the end. Yeah, so what happens is that first of all, bromine, as soon as it approaches this pi electron cloud, it's going to get dipoles generated on it. And because of that, this is going to attack this, pushing the electrons further away. So that's the start of the reaction. In the next step, I have a carbocation set up, and the more likely product is this carbocation. Of course, I can take a different route and get a carbocation here. In this case, this gets a BR. In this case, this gets a BR. There is the other BR with the lone pair, and there's the other BR over here with the other lone pair. This is bromide now. And this will attack this. Notice that I'm always drawing curly arrows from where electrons are, lone pairs or pi electrons, both of them. So it's important that you do that. And now what happens next is that the carbocation gets bromine and you are going to get two bromines added to both the carbons, and the product is going to be the same in both cases. So we have uh, 1,2-dibromo propane. Okay, so that's what we get. Uh, Now let's try to do the same thing, but what if I had this thing, but in aqueous solution? If I had the same thing in aqueous solution, what will happen? Uh, Here's the thing. In an aqueous solution, if I had this thing, and of course there'll be a double bond here, and bromine can still come over here and get the slight positive charge, slight negative charge, and this pi electron will still attack it, pushing the electrons away. All of that will happen. But let's look at what happens in the intermediate. The moment I get an intermediate, and I'm drawing this intermediate now, I have water molecules as well. And water molecules will also ionize. And it is possible that this carbocation gets attacked by the lone pair on oxygen. Because to be honest, it was the lone pair on bromide over here, that was attacking it, right? So why not the lone pair on water? If it is possible to create a hydrogen bond with it, why not attack a carbocation? And yeah, this will attack it. So while there is bromide and bromide has its lone pair and there's a negative charge, this can still attack. And what happens now is when this attacks, this hydrogen ion gives its electrons to this, although you're not supposed to show that diagram. And then what happens is that you are going to end up with one bromine, but the other is C with OH, because the OH went there. And what happens to H? Because the H has given its electrons to oxygen, it forms HBr. Because that hydrogen just becomes a positively charged thing, and that may it can attack it. So bromine, the bromide will instead attack this one. And when it does that, the chain continues. So it's not always possible to get 1,2-dibromo products. You can also get alcohols if you have water present. And if we can do that with water and bromine, why not just do the whole thing with water? We can do that. If I take ethene, for example, and I bring water close to it, or at high temperature at least, what can happen is that the bond on water is polar. There's slight negative here, slight positive here. So this can attack this. And when it does that, the electrons go towards oxygen. Obviously, they're being pushed away. So you are going to get a hydrogen here, a carbocation there with an OH with a negative charge. So no wonder this then attacks this, and we get what we wanted to get, ethanol. And we have seen this in O levels. So what are we doing? What are the conditions for this? First of all, this is not plain water, this is steam. And secondly, it doesn't ionize unless it is impure. So we try to add dilute phosphoric acid, a weak acid. We don't want the acid to start reacting. So we keep a weak acid which doesn't ionize fully, but still allows water to ionize to a greater extent. We need it to react fast, so we keep a high pressure and temperature. And there you go. We've done it. Electrophilic addition to form alcohol. You don't have to just create ethanol. You can create propanol. You can create prop 1-ol, prop 2-ol, but 1-ol, but 2-ol, or a number of different isomers of different compounds. Again, same thing. Let's try to do a reaction. Let's say I have this compound. Try to add steam to this and make both the products. Yeah, so what you have to understand is where the carbocation is more likely to form. There is two candidates. this carbon, which is a tertiary carbon, it is attached to 1, 2, and 3 carbons, and this one carbon, which is attached to 2 other carbons. Okay, so this is a secondary one, this is a tertiary one, and we know that tertiary carbocation is more stable. Okay, and that's what happens here. The major product will be formed from the tertiary carbon, and that is going to get the more negative thing. I'm using Markovnikov's rule, and the reason it works is because you have more stable carbocation. So the more negative thing in water basically is H plus and OH minus when it breaks down. So you're going to get OH here, and the other thing is going to get hydrogen. So that's the possibility. You're going to get 2-propanol, and of course there's methyls on both of them. The other option is that you take the second carbon as the carbocation. Okay, and sorry, this is not propanol, this is butanol, and this one gets the OH, and this is going to be the minor product because in presence of a tertiary carbon, second carbon has little chance or minor chance that it will get the more negative thing. So this is major product because it has tertiary carbon, so tertiary carbon will do it.
Yes, sir.
All right, let's try to do one more. Let's say I'm reacting this with water. What alcohols can I get? Try to come up with as many isomers as you can. So if you're able to do that, then I would suggest that you try to come up with as many alkenes as you can, and different kind of alkenes like 3-carbon alkenes or 4-carbon alkenes or butene or something, and try to add bromine molecule or HBr or HCl or hydrogen or chlorine, and try to figure out what different products will you get and can you apply Markovnikov's rule on that thing. If you're able to do that, then you're done with the 4-mark question that they can ask on addition. We have oxidation left for alkenes, but we'll study that on the next class.